I have about 10 slides on the problem of Bell's inequality and Bell correlation and the status of Bell correlation in algebraic quantity theory. I'd like to be quick so that we have time for the next lecture as well. But it's an important and interesting issue. And here is the main definition with which we can start, namely the definition of Bell correlation between two commuting von Neumann subalgebras of the Neumann algebra in a particular state. It's the supremum of this correlation here. The supremum is taken over all self-adjoint operators here with norm less than or equal to 1. This definition is irrespective, or it is outside of quantity theory, makes sense for general von Neumann algebras. And this is the kind of correlation which we will investigate in the context of quantity theory, where these von Neumann algebras will be local von Neumann algebras in a net, and the interesting cases, of course, when they will be von Neumann algebras associated with regions which are space-like separated. But before turning to that, a couple of general statements about the Bell correlation. Summers and Werner have shown that there's an a priori bound on this Bell correlation, which is the square root of 2 in the category of C-star and von Neumann algebras. And then once you have this definition of Bell correlation, you can define Bell's inequality as this inequality, namely when the Bell correlation is less than or equal to 1. This notion has a history which I won't go into. If you know a little bit the history of the problem of hidden variables and Bell's work, then you recognize immediately that this Bell correlation is defined on the basis of some developments in connection with Bell's inequality, which I assume to be familiar for everyone. Now, another definition here, which is very natural then, if this is Bell's inequality, is the notion of Bell correlated state. The state is called Bell correlated if this Bell correlation is strictly greater than 1. And you say that the state is such that it violates Bell's inequality maximally if it is equal to its maximum value, which, as I said, was the square root of 2. A state is called a product state across these two sub-von Neumann algebras if the value of the state on two observables, on the product of two observables from the respective subalgebras, factorizes the product of the expectation values of the observables. Now, here is a proposition which characterizes the classical situation, namely if the two von Neumann algebras are such that any of them is commutative, or if it is the case that the state is a product state across these two von Neumann algebras, then the Bell correlation is equal to 1. It's another way of saying that is that the state satisfies Bell's inequality in this case. And again, there are two such typical cases: when the state is a product state across the algebras, or when any of the algebras is commutative. Any of them commutative is enough. On the other hand, if we are in the truly quantum case, namely if none of them is commutative, then Bell's inequality is violated. The more precise statement is here. It was proved by Werner and Summers in 1986. If you assume that the two von Neumann algebras are acting on a Hilbert space and they have the Schlieder property, then if none of them is commutative, then there exists a normal state which violates Bell's inequality maximally. Here's the definition of the Schlieder property. It's an independent property. It says that the product of the two observables x and y is not equal to 0 if none of them is equal to 0 and when they are from the respective von Neumann algebras. So what this means that in the typical quantum case, when neither of the observable algebras are commutative, then there will always be states that violate Bell's inequality maximally, no matter what kind of phenomenal algebras you're dealing with. So this already entails violation of Bell's inequality in quantum theory, as I'm sure you anticipate, because if you have a net and if you have two phenomenal algebras associated with space-like separated space notations, they are not commutative. The CCR algebra is not commutative. Then there will be states across these space-like separated local observables which violate Bell's inequality maximally. So this result already entails the violation, which is stated here on this next slide for completeness. But if the phenomenal algebras are type 3, and if you remember on one of the previous slides I claimed that it's a major result of the algebraic approach, that the local algebras are type 3, at least in some cases under certain conditions which are typically satisfied, then this violation of the Bell inequality is far more dramatic. Here's a proposition which was proved by Clifton and Halverson in 2010. If you have two commuting type 3 phenomenal algebras which are assumed to be acting on a Hilbert space, and they have the Schroeder property, then the set of unit vectors in the Hilbert space, which induce Bell-correlated states on the two phenomenal algebras, is open and dense in Hilbert space, not in the unit sphere of H. That is to say, there's an awful lot of states which violate Bell's inequality maximally if the algebras are type 3. And since the local algebras in quantum theory are type 3, the Bell inequality is violated far more dramatically than in the general case, and in the type 1 case in particular. Here are propositions specified in the context of the algebraic quantum theory about the status of the Bell's inequality, Bell correlation in that theory. Here are the precise statements then. So you assume that there is a net having the standard features, then the following two propositions are true. If you have two arbitrary space-like separated double cones, then the associated phenomenal algebras are type 3 and have the Schroeder property. So in that case, there is a dense set of unit vectors that define that Bell-correlated states on these two. On the other hand, or even more dramatic is the violation, if these two space-like separated regions are tangent double cones of complementary edges, then the Bell's inequality is maximally violated in all normal states, also in the vacuum state. Okay. So again, here's the situation. If you have two space-like separated space-time regions, of which you only know that they are space-like separated, but you don't know more about them, then there's a dense set of states, dense set of normal states, which violate Bell's inequality maximally. And if these two regions are such that they are tangent double cones of the wedges, which are situated like this. This is the tangent cone. This is a double cone. This is a double cone. And I explained here that a double cone is an open region. Okay, and two are space-like separated and tangent. If their closures intersect at one point, at this point, then they are called tangent double cones. In that case, Bell's inequality is violated maximally in all normal states, including the vacuum state. This is a particular situation, and the other situation is the wedges. This is the right wedge. This is the left wedge. These are the light cones. This is the left wedge. This is an unbounded region. This is the right wedge. This is an unbounded region. And then also, if they are in this situation, tangent, then Bell's inequality is violated maximally. Now, these statements are very characteristic of quantum field theory because they don't have any counterpart in ordinary non-relativistic quantum mechanics, where you always find states in which Bose inequality is not violated. You do find on the tensor product states. There are there, and they, as the product states, satisfy Bose inequality. But in the quantum field theory case, this is not what happens. Then, if you have the tangent situation, then all normal states violate Bose inequality. Now, what is interesting here in this situation is the following. So the vacuum violates Bose inequality for tangent space-like separated regions. And for any space-like separated regions, there's a dense set of normal states violating Bose inequality. These are the previous two statements. Yet, it is not known if the vacuum state is in that dense set. That is to say, it is not known still today if the vacuum violates Bose inequality for non-tangent space-time regions. It is one of the intriguing open questions here. I myself have tried to prove something about this, and I know that Ichiro, Professor Kitajima, also has been struggling with this for a while. I don't know for how long you have tried to prove something in that connection. I've tried for about 4 months intensely. I failed miserably, and no one has been able to show that the vacuum does violate Bose inequality on strictly space-like separated algebras. Although I think, at least I do, I think many who have followed these developments think that what one should try to prove that the vacuum does violate Bose inequality in that case. Of course, it is always a big question what you try to show, but I think in this case, this is what people have tried to show. In fact, I know that the Hans Salversson and Clifton's result, which I recalled a couple of minutes ago, was the result of their effort to prove that the vacuum violates Bose inequality. They also failed, but they have been able to come up with this statement. Okay? So this is one of the open questions which you might want to work on, although it might not be advisable if you are a PhD student who is supposed to have some result and submit his PhD work within a reasonable time to start working on this, because it seems to be extremely difficult and you might not be able to prove something on it. Okay, some further comments on the violation of Bose inequality. If you have two arbitrary space-like separated, possibly tangent double forms, then the associated von Neumann algebras are both C star and W star independent, or statistically independent. This issue came up already in a little discussion with Professor Ozawa, and I'm going to talk about these independence properties tomorrow, but here we need the definition of C star and W star independence just to make a point. So I'm recalling here the definition of C star independence and W star independence. Two von Neumann algebras are C star independent if any two states, phi1 and phi2, on the respective algebras NV1 and NV2, have a joint extension into a state on the generated von Neumann algebra. And they are called W star independent if any two normal states, phi1 and phi2, on the respective subalgebras, have a joint extension to a normal state on the generated algebra. Now, it is also known that in the case of C star independence, there exist joint extensions which are product states across the two algebras. Okay? Note that I did not say that the extension is normal. I didn't say that, but there exist extensions which are product states. The point here is the following then concerning the Bose inequality situation, is that if you are in the tangent regions, which are space-like, tangent but space-like, then you have the following situation. Any two normal states, because of the W star independence of these algebras, any two normal states have a joint normal extension. W star independence and A star. Okay. But that normal extension cannot be in a product state, because if it were, then it would satisfy Bell's inequality, but it doesn't, because all normal states violate it. On the other hand, any two states have a joint product extension, none of which can be normal. It's curious, it's strange. This is a very, very crazy situation, okay? You have two regions, tangent double cross, okay? And the following is the truth. No matter how you give me two normal states, I can extend it to a normal state to the generated algebra, but that extension cannot be normal. I'm sorry, I can extend it to a normal state, but the extension cannot be a product state. Okay? On the other hand, no matter how you give me two states, I can have an extension which is the product state, but that cannot be normal. Okay? A very curious situation. I'm not quite sure what to say or think about this. This is why I put this question. Is there something to be explained here? This shows a strange behavior, a very subtle distinction between normal and non-normal states, okay, in relation to this tangent situation. Okay, these are the couple of slides which are left over from the previous talk, so let me just summarize this lecture here. I claim that algebraic quantum field theory is a quantum theory that incorporates the ideas of locality and relativistic causality using the mathematical machinery of C-star and W-star algebras. And the theory is specified axiomatically, and the axioms have a number of mathematically both deep and physically, philosophically intriguing, I claim, consequences. What were these? Well, one was that the notion of particle as a strictly localized entity, localized in bounded space-time regions, is not a maintainable position, it's not a maintainable concept. That was the consequence of Reich-Schlieder theorem. And the other was what I had just discussed, namely that the Bell's inequality is violated in that theory, and that entails that there's correlation between observables which are localized in space-like separated space-time regions. And it is important to realize that to date there is no model of the axioms in four-dimensional space-time that could be interpreted as describing interacting fields. So that's perhaps the compact summary of lecture number 3, I'm sorry. So let's go to number 4, lecture number 4. And this is devoted to the topic of causal completeness of quantum field theory. To be more precise, devoted to the status of the so-called common cause principle of quantum field theory. So here's the outline of what I tried to do in the somewhat truncated time in 1 hour I have to be fast. I might skip a couple of things in order to fit everything. First, I will talk about the common cause principle in general, the common cause principle and the causal completeness notion. I will define a notion which is due to Reichenbach's notion of common cause in classical probability spaces first, and I present a couple of propositions in this classical context. They are interesting in their own right, quite independent of quantum field theory, and there are open questions there which you might want to know about. And then I return to the notion of causal completeness, the notion of common cause, and the causal completeness notion related to that in a non-classical probability framework. Again, that's still not within the framework of quantum field theory as such, but it will be, of course, related to quantum field theory because that's a non-commutative probability theory, as I claimed in my second talk. Then I will raise the issue of causal completeness of quantum field theory in the general sense, will define the notion of common cause, which is local in quantum field theory, and then I present you a proposition which is not satisfactory, but that's the only thing which we know at this point, namely that weak inversion of the common cause principle can be proved to hold in quantum field theory. And then there are some very recent results about the status of the common cause principle in lattice quantum field theory in 2 dimensions, and I'd like to show you what these results are. Namely, the weak common cause principle, which holds in the full 4-dimensional non-discrete case, can be shown to be violated in the discrete case. On the other hand, there's a modification of the notion of common cause, bringing up certain features of the common cause in a non-commutative context, which saves the common cause principle in the sense that one can show that the weak inversion holds in the lattice quantum field theory in 2 dimensions. So that's the outline. And here is first the notion of common cause principle. This principle goes back to Reichenbach. Remember Reichenbach, I mentioned his name and his views in my first lecture. He's a major figure in history of philosophy of science, and he formulated this principle, compact version of which is the following: there's no correlation without causation. Explicitly, this means that if you have 2 events which are probabilistically correlated, then either it is the case that there is a causal connection between the 2 correlated entities that is responsible for the correlation and explains it, or if this is not the case, if it can be excluded, then there is a third something, a Reichenbachian common cause, which brings about the correlation and explains it. Okay. So this is a metaphysical principle, a philosophical principle somehow, which is a claim about the causal structure of the world, and it says that if you see correlation, and you do see correlation in the world many times, then the world, there are only 2 ways the world can be. One way the world can be is that the correlated entities are somehow correlated because they are causally related, or if this is not the case, then there is something which is in the history of both of these, in the past history of these correlated entities, which is responsible for the correlation. Okay? Now this principle, like any philosophical principle, has been very extensively discussed in the philosophy of science literature. Is this true? Is it not true? Is it reasonable? Is it not reasonable? And the general consensus is that this principle is threatened essentially by quantum correlations in the quantum world. The quantum type of correlations, the EPR correlations, and specifically the correlations which quantum field theory predicts are such that they don't have a causal explanation. So the whole research, which we also have done, and some of you also, is related to this issue. Is it true that the common cause principle really is violated? It's not by quantum theory, that it is not valid in quantum theory. That's the background of the whole issue. Now, let's assume that the principle is valid. Then it's a very natural question to ask whether our theories are causally complete, can comply with this principle in the sense of being causally complete by providing that causal explanation which the principle says should be there, either in terms of a causal connection or in terms of a common cause. And the main message of this talk or this lecture is that causal completeness of probabilistic theories in general is a non-trivial feature, but it is possible to have it. And the causal completeness of the particular theory you're talking about in the algebraic quantum field theory is essentially an open problem. Okay? We don't really know what the situation is. I think the situation is, again, very intriguing. I have more to say about this in the end, what possible positions one can take in connection with this issue in light of the available results and in the light of the efforts which have been devoted to this problem. Okay, so let's go into the details. That's the main message. The main message being, again, that we don't know what the situation is, and certainly quantum field theory cannot be considered as a theory that provides evidence against the common cause principle, not at this point. Here's the definition of a common cause, which is at the heart of this whole issue. Namely, if you have a classical probability space and you have a correlation in it, then between two events A and B, then a third event is a common cause of the correlation if it satisfies these four independent conditions. What are these conditions? Well, the correlation disappears in the probability measure, which is the probability measure obtained from the original one by conditionalizing on the common cause. Because here this means that these two events, A and B, are probabilistically independent with respect to the conditional probability measure, conditioned by C. The same is true for the probability measure, which is conditioned by the orthogonal component of C, the common cause. And the probability of A happening on condition that the common cause is present is strictly greater than the probability of A happening on condition that the common cause is absent. And similarly for B. These two conditions are called the statistical relevance conditions. The common cause is statistically positively relevant for A and B to happen. And these are called the screening of conditions. This condition is sometimes expressed by saying that the common cause screens off the correlation between A and B, and similarly, the absence of the common cause screens off the correlation. Now, you might want to ask, why this definition? What's the rationale behind it? There is a rationale behind it which I'm not able to detail here. There are intuitively appealing examples of situations, classical examples, in which an explanation of the common cause along these lines seems to be intuitively attractive. Okay? I'm not giving you, I don't have time to give you examples, but if you have a look at Reichenbach's book, The Direction of Time, which was published in 1957 after he died, you find examples there which illustrate the reasonableness of that definition. So I just take it now, formally, that's the definition, formally it's a precise definition, and the question is then whether our theories are probabilistically complete in the sense of containing common causes of the correlations they predict. That's the issue. Okay. Now, the definition of causal completeness. Remember what the notion of common cause principle was. It said that if there is correlation, then either there is a causal connection, or if there is no causal connection between them, then they're supposed to be explained. The correlation is supposed to be explained by a common cause. And the causal completeness definition expresses that. Suppose you have a causal independence relation on the set of random events, then as probability theory is said to satisfy the common cause principle if it is causally complete in the sense that it contains a common cause of every correlation which is between causally independent events. Seems reasonable, right? So a probability theory is causally complete if it can give you a common cause explanation of every correlation which is between causally independent events, because of the correlations between causally dependent events, if there is such a correlation, are explained by the causal dependence. Okay, so that's the definition, and then the problem is, under what conditions is a probability theory causally closed? There's a lot of room here to play with, and this notion can be developed in many ways. And you realize also that one can make a probability space causally complete in a cheap way, namely just by defining the causal independence relation in a particular way so that it makes the probability space causally complete. Namely, you just define A and B causally related, that is to say, you say that the causal independence condition does not hold whenever A and B are correlated, but there's no common cause in the space of the correlation. But of course, this is not what you
are interested in this cheap way of making theories causally complete for a number of reasons. You need a disciplined definition of causal independence. Again, I said there's a lot of room to play here with it. So a lot depends on how you define the causal independence relation. And a very weak condition of the causal independence notion is the following intuition, that if A and B are causally independent, then you should be in the position that you are not able to infer either the occurrence or non-occurrence of B from the absence or presence of A. And conversely, from the presence or absence of B, you should not be able to infer the occurrence or non-occurrence of A. This seems to be a minimal condition. Otherwise, you would not claim that the two events A and B are causally independent. Now, two events in a Boolean algebra are logically independent if these conditions hold. That's more or less standard definition. A doesn't entail B, not A doesn't entail B, A doesn't entail not B, not A doesn't entail not B, and so on. None of these, all of these are independent somehow. And two sub-Boolean algebras of the Boolean algebra are called logically independent if any two elements in them, which are non-trivial, which are not contradictions, are logically independent. Another way of expressing this feature is to say that two sub-Boolean algebras are logically independent if no matter how you take one proposition from one and another from the other, the two can be jointly true in some interpretation. That's the content of logical independence of two sub-Boolean analyses. And then it's a very natural definition to say that the probability space is causally closed with respect to logically independent sub-Boolean analysis if it contains a common cause of every correlation between those elements which belong to these logically independent sub-Boolean analyses. So we have now a more specific notion of causal completeness, of causal closeness, which intuitively is, I think, defensible. And the question is, which spaces are causally closed in that sense, and which spaces are not? What can we say about this? And the first proposition which I can present to you is that a finite probability space is not causally closed with respect to every pair of logically independent Boolean subalgebras. Again, if you have a model of your verb, of your physical situation, which is such that the probabilistic model is finite in the sense of the Boolean algebra being finite, as a finite cardinality, finite number of elements, then that probability theory is not causally closed with respect to every logically independent Boolean sublattice. Okay? There's a small print here. Curiously, there is one exception, which, however, I don't know what to do with. The Boolean algebra, which is generated by 4 atoms with a uniform probability measure on it, is causally closed with respect to all Boolean subalgebras, which are logically independent. But that just seems to be a coincidence, a mathematical coincidence. And I don't think it has any philosophical or physical or whatever significance. So this was proved in 2004 in this little paper in Foundations of Physics by a student of mine and myself. His name is B. Janisch. B is in red. I'm working with his brother as well, who's a mathematician, with Zola and Janisch. And so I have drawn a whole family into this business, unfortunately for them. So this is why this B is in red. Another proposition which is true is that in every finite probability, there exist logically independent Boolean subalgebras with respect to which the space is causally closed. So it cannot be closed with respect to all logically independent sublattices, but there are sublattices with respect to which it is causally closed. Another proposition here is that if you have a finite probability space which is causally not closed, which is typically the case with respect to a pair of Boolean sublattices which are logically independent, then that space can be extended in such a way that the extension is finite and is causally closed with respect to the logically independent pair consisting of the homomorphic images of S1 and S2. So suppose you have a probability space which is causally not closed, containing a correlation between two elements which are causally, which are logically independent, and there is no correlation, or no common cause for them. It's a very natural idea to ask then, can it be the case that this probability theory is embedded into a larger one, such that the larger one already has a common cause of the correlation? By a larger one means a space with a Boolean algebra and a measure on it, such that there is the Boolean algebra embedding of the small space into the large one, which preserves the probabilities. Okay? It's a very natural definition of extension. And the claim here is that indeed this can be done. So any small space can be extended into a larger one, which is still finite, such that the larger one has an explanation of the correlation in terms of the common cause. The philosophical motivation behind it, or physical motivation, you don't have to call it philosophical, is that maybe your probabilistic model, which predicts a correlation but is not able to explain them, is just too small. You have not taken into account enough parameters, enough events in the verb, and if you had done that, maybe your theory, your richer theory, would be rich enough to give an explanation of the correlation. It's a very natural idea to ask whether this is possible, and the claim here is, yes, this is possible, which is a kind of consolation, if you believe that the common cause principle is a valid principle. But even if you don't, this has heuristic consequences, heuristic value, because it tells you, look, you have designed this probability space to describe a certain phenomenon. This probability theory gives you a correlation, but you're unable to explain within that theory the explanation. Maybe you should have another theory, which is a better one, a larger one, richer one, finer one, which is capable of giving you an explanation of that correlation. And this proposition says that indeed this thinking is a good thinking because it's maintainable mathematically speaking. The next issue, okay, so far at the previous slide contained propositions about finite probability spaces. The finite probability spaces are discrete in some sense. They are the opposite of what monatomic probability spaces are. Monatomic probability spaces, monatomic in the sense of measure theory, are the following ones. A probability space is purely non-atomic if the following is true. For any A which has a non-zero probability, there exists another event which is smaller, which had a smaller probability, strictly smaller. So no matter how you choose an element in that probability space which has a finite, a non-zero probability, there will be an event in that probability space which has smaller probability. Okay? There is no smaller probability event in that probability space. Okay? And if this is true, then this space is called non-atomic in the measure theoretic sense. Notice that non-atomicity can also be defined for the algebra itself, and non-atomicity in the measure theoretic sense and non-atomicity in the algebraic sense are different concepts, although they are not independent, they are not unrelated as we will see, but they are conceptually different. Here's an example. The normalized Lebesgue measure on the 0-1 interval is purely non-atomic as measure space, but the Lebesgue measure of the sets form an atomic Boolean algebra because the one element sets, which are closed sets, are in the Lebesgue measure of the sets. Okay, so it's atomic as a Boolean algebra, but the measure space is non-atomic. a related definition is the measure theory atom, a p atom. An element is a p atom if it has non-zero probability, and for all elements which are smaller, we have that the probability of that element is equal to 0 or the probability of the element itself. Okay. Why is the issue of non-atomicity and atomicity relevant? Well, anticipating what's coming, because these are the opposites for the finite probability space. And indeed, somehow, it turns out that non-atomic probability spaces are better behaving from the perspective of the common cause principle. Namely, what turns out is that non-atomic probability spaces will be common cause complete. What I mean by common cause completeness is the following, that any correlation in them, no matter what, no matter between where the correlated events belong to or not, they will have a common cause. The correlation will have a common cause. To be a bit more formal, if the causal independence relation holds for all correlated events in that space, and the space is causally closed with respect to that relation, then I call it common cause complete. So if this holds for all correlated pairs in the space, then causal closeness with respect to that thing is called common cause completeness. And here's a proposition about non-atomicity. This shows why the non-atomicity is relevant. That if you have a non-atomic probability space, then it is common cause complete. So in non-atomic probability spaces, we are all right. They are extremely rich in events, so rich that every correlation has an explanation in them in terms of the common cause. Now, this points to the general problem of the role of non-atomicity and atomicity in connection with the common cause principle. Because as we have seen, probability spaces with finite Boolean algebras are not purely non-atomic, measured theoretically, and they are not common cause complete. Whereas the purely non-atomic ones are common cause complete. So the question is, what precisely is the role of measured theoretic atomicity in common cause completeness? Clearly, one fears that measured theoretic non-atomicity somehow is directly relevant for common cause closeness. And indeed, that turns out to be the case. Here is a proposition. This is with Zolan Janisch, the brother of the other guy with whom I have published that paper. And this is in philosophy of science. The following characterization of common cause completeness can be given. A probability space is common cause complete if and only if it has not more than one p atom. Or putting it differently, a space is common cause incomplete if and only if it has more than one p atom. So you cannot expect, essentially, what this says, that common cause complete spaces are purely non-atomic. This is what essentially is true. So if you have a Boolean algebra which has a finite number of elements, then it's not common cause closed. Finite probability space typically always contains, with the exception of that particular one I mentioned, always has more correlations than it can explain with the help of common causes only. Now, these common cause completeness, closeness result also makes it possible to show something which is a strengthening of the proposition which I stated before, which was that if you have logically non-independent sublattices in a finite Boolean algebra, and it is not common cause complete with respect to that, then you can extend it in such a way that the extension contains a common cause for that particular correlation. There's a more general, more powerful statement to that effect, and it is the following. Every classical probability measure space is embeddable into a purely non-atomic probability space. And since purely non-atomic probability spaces are common cause completable, every classical probability measure space is common cause completable. The significance of this is that the strategy which